how we come to understand the natural world. Can you guys see that in the back okay? Okay. We're looking at how we come to understand the natural world. We want to start to explain the things we see in the natural world, and we want to use those explanations to help make predictions. So there's a lot of kind of talk about what the natural world looks like, and how there's this kind of coming to a head between like faith and reason, right? And how God is not involved in science, and that couldn't be more far from the truth. Yeah. I can try. When we're talking about science and its involvement in the natural world, we've got to understand that God created the natural world, right? Therefore, it is filled with truth, and he's allowed science to help us unfold or discover those truths, right? God set up the natural world with all kinds of patterns and all kinds of things that he's allowed us to discover. And so people think there's this disconnect between science and faith, and that's not true, right? There's a lot of things that are explained only through God and his works, right? So we've got to, while we're thinking about what the natural world looks like and how it is encapsulated, we've got to really understand that like God created that and has allowed us to be able to discover these things within the natural world, finding all of these patterns he laid out and all of these things that he allowed us to discover. So, all right. We deal with the natural world in science. We collect and organize information in a careful, orderly way, looking for patterns and connections between events. Okay? We look for those patterns that God set up. We look for how these things connect. Okay? There's going to be several words that come up in this first slide that I want you to try to see what are some of the patterns just on this first thing that describe science. I want you to be thinking about that. There's a couple words that will come up over and over again that really are important. Okay? So we deal with the natural world, we collect and we organize information. We think that explanations need to be tested, right? We don't just make assumptions. We want to test these explanations, and then we want to use the evidence we get to really examine those. Okay? So scientists have to not only ask these questions and make these conclusions, but they got to be evidence-based, right? Because there's a difference between a conclusion and an assumption, right? Assumptions are kind of guesses, and conclusions are evidence-based. Okay? Scientists is an organized way of using evidence to learn about the natural world, right? It's just putting everything about that natural world in an organized and orderly manner. So I want you to look at these sentences that describe science in general and see what are some words that keep popping up. Okay, raise your hand if you see words that keep popping up. Yeah, Leia. Organized, good, right? I think that's one of the most important one. We collect and organize data. It's an organized way of doing something, right? Very good. What else? Yeah, Sophia. Evidence. Good. We've got evidence right here. We've got evidence right here, right? So we're not basing things just on thought or feeling. We're basing things on evidence that has come up. Yeah, what else? Yes, Sophia Riley. Natural world. Very good. Right? We're looking at the natural world, right? In comparison to the supernatural world, right? We know that God has created science and has created the natural world to allow us to investigate, but we're not overlapping that necessarily in our stuff, in our evidence-wise. But okay? What other thing do you see? The other word that I wanted to point out, and maybe it's not as much, maybe it's not as repetitive, but it's the word patterns, okay? That's a lot of what science is trying to develop and understand the patterns that come up. We'll see that a lot in chemistry and physics, okay? The periodic table is full of patterns. It's designed to look that way so that we can see patterns within the elements, right? The equations we use for physics are designed so that we see patterns in motion, right? That's how these things are designed. So yeah, it's interesting. Yes, Henry. We want to make sure that we explain and explanations, right? Those two things are both used a lot, right? We not only have the evidence, but we give a full explanation for that evidence. So good, very good. All right. How do we do science, right? How do we do science? Science begins with a what?
Idea.
An idea. What's another word? A thought. A what else? A question. Good. All very good. It begins with an observation. Okay. Any of the things that you guys said, though, would have been fine as well. Right? An idea, an observation, a thought, a question. Any of those would have been fine. Okay? Observation is the one that we use because it has to be observed for us to really ask the question. Right? I don't just ask a question without observing something that piques my interest. Right? I've got to have something that I am actually trying to observe and trying to think about here. Then, after I've got an observation that leads to a question, I've got a process I go through in which I gather information and then I process them. I analyze them. What's that method called? Or what's that process called? You can say it. It's called the scientific method, right? So, once we start looking at our observations and we start to decide what's our question that we need to answer, we have to start collecting data. Okay? And all that data in its most simple form is the information that we gather. Okay? The information that we gather. There's two different types of data that we can collect. Does anybody know what those types of data might be called? Okay. Two types of data. The first type is called quantitative data. Is that a new word for us, or have you heard that before? Okay, it's new. Quantitative data. What do we think that root means? It looks like quantity, right? Which means quantitative data deals with our numbers. Any sort of data that is counted or is measured is considered quantitative data. So if I'm writing down how long something is, how hot something is, how tall, how short, how fast, how slow, any of those things that involve numbers are considered quantitative data. Okay? The opposite side of that spectrum is called qualitative data. What does that root look like? Qualitative data probably deals with the qualities of our object, of our test. Okay? Qualitative data deals with just qualities. So these are observations or characteristics that we can't put numbers to. Okay? We can't put numbers to them. Can anyone think of a couple examples of what qualitative observations or qualitative data might be? What are some things we could observe, but we can't necessarily put a number to them? I would write down a few of these examples too. Quantitative data could have been mass, volume, temperature, right? A bunch of different things. Most of what we consider data is quantitative, right? Most of what we think about as being data is quantitative. But we also have this other side of the spectrum, which is called qualitative data. Okay? Those are two types that you need to know, right? You'll need to make sure that you understand the difference between those two things. Okay? And you might have to be able to give examples of those things. Okay? All right, so here's a basic. We're going to walk through the 5 steps, and then we're going to dive into these 5 steps a little bit more deeply, okay? So the scientific method is a series of steps we use. It starts with us asking a question, okay, or forming an observation, then forming a hypothesis, then designing a controlled experiment, recording results, and drawing conclusions. So those are the basic 5 steps. Sometimes you'll see the scientific method drawn out into even more steps, right? Where they really break down things really, nitpicky, I guess. These are the 5 general, okay? And we'll dive into them a little bit more here. But those are the 5 in general. Question. We've got to identify what question we want to ask. These are just some examples of those types of questions. How much water can a root hair absorb? Why does a plant stem bend toward the light? And what effect does temperature have on heart rate, right? Those are all questions that you could ask that could lead you to an experiment. Questions that prompt experiments or this first step, those questions can be very broad or very specific, right? You can think about them a lot of different ways. So those questions can be either very broad or very specific. If we need to form a hypothesis, what's kind of the elementary definition of a hypothesis? Somebody tell me, what do you think the definition of a hypothesis is? Yeah, Ty.
Educated guess.
An educated guess. Very good. What other kind of definitions could we give for hypothesis? What are other catchphrases we have about hypothesis? How should hypothesis be written? In an if-then statement. Have you heard that term before? We write hypothesis in an if-then statement. Okay, those are 2 things that are correct about hypotheses. Okay, it's just an explanation or a possible explanation to our question. Okay, we also call it an educated guess, right? Because we want it to have some sort of valid content behind it. We're not just taking a guess, but we want it to be an educated guess. Okay? It has simply still a prediction. Although it might be an educated guess, it's still a prediction. You have to complete the test to be able to figure out, is it valid or is it invalid? Is it proven or is it disproven? Right? You still have to follow through on that. We have to write the hypothesis in a way that is testable. And so generally we give the guidelines of, we write them in if-then statements. If I whatever, then this will happen, right? If I add more water, this will happen. If I raise the temperature, this will happen, whatever, okay? That's what hypotheses are generally written on. I'm not going to say they have to be written that way 100% of the time, but in general, we want them written in a testable way, okay? If it's considered testable, the evidence will either support or not support that claim, okay? So when you collect the data, it's got to either show support for your hypothesis or it's got to disprove your hypothesis. We don't collect data that doesn't have anything to do with our hypothesis, right? That would be silly for us to collect data that doesn't apply to our hypothesis, okay? All right, the next slide, I put a couple more things up about hypothesis, but I really don't think you need them because they're exactly what you just wrote down, so I'm going to just skip over this slide, okay? So you can just skip that one. All right. Let's look now at step 3 in designing what's called a controlled experiment. Do you know what a controlled experiment is? Okay. A controlled experiment has to deal with how you manipulate the variables within an experiment. Okay? So first and foremost, the things that can change in an experiment are called variables. Okay? The things that we can change or the things that we don't change are called variables. Okay? Examples of variables could be us changing the temperature, how often we measure time, how often we measure something, right? If it's every 5 minutes or every 5 months, right? That's a variable. The amount of light present, amount of the concentration of our solutions. It can be anything, right? Variables can be anything. But in a controlled experiment, we only manipulate one variable at a time. Okay, we only manipulate one variable at a time. If we don't, then we don't know which variable is causing the result change. Okay, so I want you to think about an experiment here with me in just a minute, okay? We're going to kind of use this as an example as we walk through. Let's say that I want to measure how fertilizer affects plant growth, right? A very common scientific method type of experiment. Okay, I want to see how does fertilizer affect the growth of my plants. Okay? So what I would probably do to set up my experiment is I have one plant that doesn't receive any fertilizer, right? It just receives regular water. And then I have another plant that receives like a little fertilizer. And I've got another plant that receives like a medium amount, and another plant that receives a lot, right? So I've got these set up so that I can see what happens when it receives nothing, what happens when it receives a little, a medium, and a lot amount, right? Does that kind of make sense? Can you visualize what I'm talking about here? Okay. But if I go about my experiment and I not only am watering the plants with the amounts of fertilizer I said, but if I'm moving them to different rooms so that some get more sunlight than others, if I'm watering some more often than others, now I no longer have a controlled experiment because I'm changing the fertilizer amount, the water amount, the sunlight amount, right? I'm changing all of these different things that could affect plant growth, and so I no longer have a controlled experiment. Does that kind of make sense? If I wanted to do a controlled experiment like that, I would have to keep everything else the same. So the type of plant would have to be the same. The type of pot I put it in would have to be the same. The location of all these would have to be the same. The time of day I water them, the amount of water I give them, all of these things have to be the same. The only thing I would change would be the amount of fertilizer that goes on each plant. Does that kind of make sense? That would be considered a controlled experiment because everything stays the same except the one thing I'm testing. Okay? All right. So, in a controlled experiment, we only change one variable at a time. Everything else should be controlled. All the other variables should be controlled. Okay, so in my plant example, the variable I'm changing is the fertilizer. Everything else that is controlled is the pot, the plant, the soil type, the water amount, the water location, the plant location. All of these other things that could affect plant growth, they have to stay the same. Okay, questions about that? Okay. An experiment with, that's based on a comparison. It's based on how we deal with what's called the control group and the experimental group. Okay, so in my plant example, my control group is that single plant that receives no fertilizer. That's my control group, right? That's what happens without my variable having an effect on it. The experimental group is all the other plants I have that I'm giving varied amounts of fertilizer to. Okay, so your control groups don't necessarily have to be the same sample size. That probably is better. But in my plant example, the plant that receives no fertilizer is my control group, and the other set of plants that receive fertilizer, those would be considered my experimental group. They're identical except for the fertilizer. The control group serves as the comparison. So here's what happens without fertilizer, and then we see the effects that the fertilizer has. Okay? The experimental group shows the effect of the variable that's being tested. So in my plants, it says, is little fertilizer best, medium fertilizer best, lot fertilizer best, whatever. Okay? All right, we're going to look at this example here. I wrote up this example, and I left out one key component, so I'm going to write that in as we go. In order to test the effectiveness of a new medicine, 50 volunteers are selected and divided into two groups. One group will be the control group, and the other group will be the experimental group. Both groups are given a pill to take that is identical in size, shape, color, and texture. Except I forgot to write down that the experimental group will receive the medicine in their pill as well. All right, that's kind of an important piece for you to know. Okay? So we're testing this new medicine. We've got 50 people split into two groups. The pills look the same. They're the same size, shape, texture, and color. The only difference is that internally, one of the groups of pills contains the medicine that we're testing the effectiveness of, and one of them does not. Does that make sense? Okay, so let's look at what happens here. Give me some description of what happens in the control group, or what is the control group in this case? Describe the control group, describe the experimental group, which variables are kept constant, and which variable is manipulated. Which variable is being changed. Okay, so tell me what's in the control group. Yes. The control group is how many people? Half of 50, right? 50 people are divided into two groups. So it's 25 people. Does their pill contain the medicine or not?
It does.
Not in the control group, right? The control group is the one we're leaving alone. We're not manipulating that group. So they do not receive the medicine. But do they know they're not receiving the medicine? No, because their pill looks and tastes the same probably, right? Everything else about the experiment has to be the same. The experimental group also has 25 people. They do receive the medicine that's in the pill they take. Okay, so now let's think about some things that aren't even listed here. What are variables that are kept constant about the pill itself, right? What are things that it listed that stays constant? Yep, size, shape, color, what did it say? And texture. Okay, those are all things that are kept constant. But let's think about some other things that aren't even listed that might be kept constant. Do you think one group receives the pill more often than the other? No, right? So frequency has to remain constant. Frequency, I think I spelled that right, okay? Frequency has to remain constant. What about, like maybe the pill has to be taken with food. Do you think they receive the same meal? Yes, right? Let's say if that has to be taken with food, they would have to receive the same meal. What about the time of day they receive the pill? Does that matter? Yes, right? It might not seem like it does, but it does. So the time that they receive the pill, all of that stuff has to be the same. Okay? But what's the one variable that is being changed? What's the one thing that we're looking at?
Medication.
Right. Is the medicine present or is it not? Right? In the group that's receiving the medicine, that's really what we're going to be measuring here. We want to measure the health outcomes of that group that received the medicine. All right. I just wrote down a few things that we talked about here as well, so we got that. Okay. In an experiment, there's variables, and there's really two types. Okay, two types of variables. One of them is called the independent variable. One of them is called the dependent variable. Have you heard those terms before? The independent variable is the thing that we control. We control the independent variable. Okay? It's the thing that we are manipulating. It's deliberately changed. So let's think about our medicine example. What was the independent variable? What was the thing that we controlled or we changed? Yeah, James. Yeah, that's right. Okay. The independent variable for that experiment was the medicine itself, right? Here's the people that received the medicine. The thing that is dependent upon that, the dependent variable is the one that we are observing. Okay, the dependent variable is the data that we collect. Okay, it's like the outcome of the experiment is what happened to the dependent variable. So in our medicine example, we would say that the medicine itself, that's our independent variable because we controlled who got the medicine. And then the dependent variable would be like the health outcome, right? Did the medicine make them more sick, less sick? Did it not make a difference at all, right? That, it would be the dependent variable. So like the health of the patient would be considered our dependent variable here. Okay? Think back to my plant example. What would be the independent variable in my plant example? What was the thing that I was changing? The fertilizer, right? And the fertilizer amount. And then what would be the thing that is the dependent variable? What was I measuring? The plant, more specifically what?
How they grew.
Yeah, plant growth, right? So I probably measured by height, how tall the plant was. I could have measured by like the number of plant buds or whatever, however I was measuring that. But plant growth would have been my dependent variable. So, very good. I think that I had up here a couple other questions, but we talked about that. In the medicine example, the independent variable is the medicine itself, and then the dependent variable is the health of the people that receive them. Okay? Okay? Once we've got our data collected, we've got to answer the question, does it support or does it not support our hypothesis? Right? Does it prove or disprove our hypotheses? Okay? That's what we're kind of looking for there. Does it prove or does it disprove our hypothesis? Pretty simple, right? We've got a lot of things that we do in this step, but that's the goal. We're going to take our data and see, does it prove or does it disprove our hypothesis? All right, then we draw our conclusion and we say, based on our evidence, right? We're going back to the very beginning where we said it's got to be evidence-based. Based on that evidence, we've got to draw the conclusion. Does it support our hypothesis or not? Okay? Then, once we've got that, we've got to repeat our experiment. We can't draw a conclusion, like a really valid conclusion, after one experiment, right? It's got to be done multiple times. If we can repeat it, and if we can draw the same conclusion over and over and over again, then you can kind of start to call that a valid experiment and a valid conclusion that you've drawn, right? If they can be repeated, and if you're getting the same conclusions over and over again, then you can pretty much call it valid.